you still in the review for forevers, the introduction phase? Cool. But then today we're definitely going to chapter 1 limits. So here we go. Let me get all of these graphs up. Let me get the double page and full screen. Can we see them all? Are they off the board? Nope. They're on the board. You can hardly see? That's okay. If the glare is kind of funny, let's go ahead and do that. If the glare is kind of funny, let's go ahead and do that. So hopefully you have this already set up in your notes. If it's in your forevers, cool, but I'm not exactly sure you want to rush and put it in your forevers either, because then you might make a mistake. I don't know about you guys, but in years past, they liked on this card to do some color coordinating. Whether you do different colors for like the trig versus the polynomial versus the, okay, you could do that, but they just kind of liked the grids being one color and the graphs being another. It's up to you. I'm just letting you know you can have some fun with your forevers. But in the notes right now, let's go ahead and go through these different functions. So first of all, let me make my marker a little bit thinner, because the thick marker is going to be kind of annoying on this one. Let's go 1 down. That should be good. All right. For the constant function, anybody know what the constant function is? It's just a horizontal line. Good. It could be up here. It could be down there. It could be on the axis itself. Just for sake of illustration, I'm going to put it up here. The function is y equals c, or f of x equals c. If y equals a constant. If y equals, let's see, what could be an example of this one? Y equals 5. Why could that graph not be y equals -1? Yeah, it's on top. It would need to be below if it was -1, right? This is another reason for color coding, right? Not that I would be like super sad or mark you wrong if you put the line below rather than above, because technically the constant function is general. But color coding is kind of nice because you have 2 horizontal lines. For the rest of them, it won't be quite as tricky. The identity function, you guys should know this one. What's the identity function? Y equals x. What would y equals -x look like? Yep, it would just be flipped. Good. Identity function y equals x, 0, 0, 1, 1, 2, 2, 3, 3, etc., etc. Y equals x squared. We're not putting points just for sake of time, even though we could put points. Y equals x squared would be what? 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. Has the vertex a minimum at the origin? Concave up parabola. X cubed also hits at the origin, has the point 0, 0. Also has the point 1, 1, 2, 2, 3, 3, but then it goes way steeper. Sorry, 0, 0, 1, 1. But instead of 2, 4 for the parabola, you have 2, 8, you have 3, 27, you have 4, 64, you have 5 and 125, you have 6 and 2, 16. Is that right? 36 times 6? I think it's 216. But it goes way steeper than a parabola. Square root of x. That square root should go all the way. I was having a little bit of difficulty getting these to look nice and pretty. Square root of x also hits at the origin. Do you guys remember what he looks like?
It's the parabola.
Yeah, parabola, but to the side. Good, concave down. It cannot go lower than 0. Why can't x be -1 or -2 or -3? Why is there nothing there? Good. Square root of a negative number is complex or imaginary. Wouldn't be there. Cubed root. Here's the funny thing. Well, number 1, he goes a lot steeper, so he's not going to be quite as tall, because you're going to have to do 0, 0, 1, 1, 4, 2, 8, no. Sorry. 8, 2, 27, 3. This one was 0, 0, 1, 1, 4, 2, 9, 3. It's like the backwards of the squares because they're inverses. These ones, they look super similar, and they're going to look super similar. 1 over x has a vertical asymptote at 0. But when negative, 1 over x is negative. When positive, when x is positive, 1 over x is positive. Oh, cubed root. I did not finish him. I am so sorry. I started talking and got distracted because I got messed up with my numbers. Cubed root. Negatives are allowed. You can have the cubed root of -8. It's -2. Or the cubed root of -27 is -3. I apologize. Cubed root. A little bit narrower, and domain is all real numbers. 1 over x squared looks like 1 over x, except the values are a little bit more squished, a little bit closer to the axes. Still has a vertical asymptote. Very important, has a vertical asymptote at 0. Sorry, that was supposed to be a straight line. That didn't work out so well. But 1 over x squared, whether you plug in a positive or a negative, what will the y's always be? Positive. Which is why this also displays y-axis symmetry, aka it is an even function. Ooh, summer packet. Even functions. You plug in a negative, and it ends up simplifying to be the same thing as if you plugged in a positive. Even functions, y-axis symmetry. Absolute value x. You guys remember him? He's the v. Oh, sorry, I could have kicked that towards you. Absolute value of x. Just take out the absolute value. Y equals x. So for positive x's, it's the exact same as the identity function. But at 0, 0, everything changes because all the negatives, instead of going down and being negative y's with negative x's, plug in a negative x, and what kind of y do you get? Positive. So hence why it flips up. When I pick up my pen, things don't match. There we go. So it's going to be the v. It's really just the identity function with the negative portion being flipped because of the absolute value. Greatest integer last year, you might want to put this off to the side. The greatest integer was also, I think he was called that. He can also be called the step function. FN, abbreviation for function. He can also be called the step function. Sorry, my hair's on my microphone. That could be bad. Step function. He's a little weird. If you guys didn't notice, I did put the cheater chart up on the board yesterday for period 6. They asked me to do it. They timed me. Took me 30 seconds. Anyone who didn't have me last year, the cheater chart, 30 seconds. You can write it on any quiz, on any test, on any assignment just from memory. Takes 30 seconds, and you can use it the whole time. It's the first quadrant of the unit circle, all the sines, cosines, tangents. Do you have to put this in your card? No. Some of you don't use it, so don't put it. Some of you do use it, so maybe put it. But anyway, that's what that is. Let me go ahead and do the step function over here. I'll do a quick version up there, but just so you guys can see the detail to it. Okay, the step function basically asks, what is the greatest integer, counting number, 1, 2, 3, 4, 0, 1, 2, 3, 4. What's the greatest integer in the number without rounding up? So for instance, 0, well, the greatest integer is 0. 0.1, it hasn't gotten to 1 yet, still 0. 0.2, still 0. 0.999999999, still 0. It doesn't go to 1 until you hit 1. So you're going to have a straight line until 1. And then as soon as you get to 1, 1.1, well 1, 1.1, 1.2, 1.3, 1.4, etc., 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 all the way up until 2, all of those numbers, the greatest integer in them is just 1. It hasn't gotten to 2 yet. So starting at 1 and going all the way up to 2. Do you guys kind of remember this guy from last year? And then all of a sudden, once you hit 2, now you can pop up to 2. And you're going to stay at 2 all the way until you hit 3. I think my example from last year as to a practical example of this would be like paying for parking in parking garages. Because they don't necessarily give you like a prorated, like, oh, you were only here 2 hours and 2 minutes? Sweet, we'll just charge you for the 2 hours. Or we'll charge you for the 2 hours plus a few pennies. They're like, oh, you were here more than 2 hours? Okay, we'll charge you for 3. So that's like an example of paying in a parking garage. Except they would be a little different. Instead of charging nothing for the first hour. No, some do that, right? Like the first hour is free. And then all of a sudden, as soon as you were there like an hour, it's like, haha, we can charge you. Although I guess if the first hour is free, maybe that would be filled. This would be open. But as soon as you were 1 second past the first hour, or 1 minute past the first hour, they start charging you. So maybe it would change a little bit. But this is the idea of the step function. So you can keep on coming back. There's a whole ending in a solid, then a whole ending in a solid. So I'm going to go ahead and put the sketch up there. But I wanted to remind you guys of what this guy actually is. Sorry, for anyone on the video, here I am. So you're going to have 0, 0, all the way up until 1. Then you have 1 all the way up until 2, 2 all the way up until 3. You can put little tick marks if you want. You can go backwards, whole ending in, whole ending in. Depends on how big your graph is as to how many of these you put on. But you guys get the general idea? Just think rounding down, kind of. Rounding down. Negative numbers rounding down is weird because you're rounding to the next bigger negative number. Like negative 0.5 hasn't gotten to 0 yet. So even though it's the same pattern, to negative 1. Negative 1.5, you to negative 2. But you're not rounding, you're actually taking, you are rounding down. It's just weird because the number's getting bigger. ln of x has a vertical asymptote at 0. That's why the domain problem why the domain problem, you might want to put a little hint. This would be a good place just to remind yourselves. For any logarithm, the inside part, the argument, has to be greater than 0 because of my visual people, because of the vertical asymptote. If it helps, you could also mark down the point 1, 0, because ln of 1 is 0. I mean, this is on your forevers, and these are good things to have in the back of your mind and be able to pull out. So even though it's in your summer packet, some of these ln things, this might be a good place to put it, because then you'll keep on studying it throughout the year and not forgetting it. You could, if you wanted to, also mark, this is going to be a little harder, E is 2.71828. In between 2 and 3, you could put like a little, if you wanted to. Once again, these extra markings are optional. But you could, around 2.7-ish, you could go ahead and mark the point E1, because ln of E is 1. It's up to you. Those are a couple things that are easy to get confused. E to the x, remember he swoops, but he's the inverse of ln, so he swoops the other way. He has a horizontal asymptote instead of a vertical asymptote. That reflection across the y equals x, that inverse property. For this one, domain is all real numbers. I guess you could write that. That's up to you. But yeah, the domain is all real numbers. The range would just be only greater than 0. Let's see, you could put the point 0, 1. And then you could put the point, I guess it should be a little bit steeper of a swoop. Exponential growth is one of the fastest types of growth. It's not the fastest, but it is one of the fastest. Only thing that beats it is factorials. But you could put the point 1e. Remember the point split. But that one's kind of easy because most of you know that e to the 0 is 1. E to the 1 is e. But you could put that if you want. All right. Now we get to fun stuff because now we have our last 4 graphs. Trig. Now, if you remember from last year, trig graphs got super messy, right, guys? So we can't put all that detail in these little baby graphs in your notes or your forever cards. But we can put enough that hopefully you have a good picture of how these graphs work. Now, some of you aren't visual, I know, so maybe it's not as helpful, but you do have to, at different points of the year, have an idea of what the graph looks like, even if you're not a visual learner. And if you are visual, we're trying to give you something to visually attach some of these facts that you have to hold on to. Sine of x, does he start in the middle or does he start at the top? Sine of 0 is 0. Good. Sine of 0 is 0. Starts in the middle. Sine and cosine both are going to go to 2 pi. Complete a full cycle to 2 pi, a full cycle to negative 2 pi, a full cycle to 2 pi, a full cycle to negative 2 pi. They're both going to go up 1, down 1. These are non-transformed, right? We could cut these into quarter cycles from last year. We could cut these into quarter cycles, which a fourth of 2 pi would be pi over 2, or a half. So we can count by halves, pi over 2, pi, 3 pi over 2. But you don't necessarily have to write that. I'm just letting you know what these little tick marks stand for, what our scale is. Sine starts in the middle, goes to the top, comes back to the middle, down to the bottom, and back up. Remember, it's just a wave. A wave that keeps on going. Cosine, what's different? He starts at the cosine of 0 is 1. Cycle. If we shift a cosine, he'll look like a sine, and if we shift a sine, he'll look like a cosine. Ooh, that's not hitting where I want it to. Okay. I'm not just going to graph sine and cosine, though, because what other graphs depend on sine and cosine? What were we able to graph on top of a sine curve last year? Cosecant, because cosecant is the reciprocal of sine, 1 over. Do you remember our tricks for 1 over? I'm going to do a different color. Here's another time that color coding. So if you have a different color, you might want to grab it out. I'm going to go ahead and use maybe green, because we can also graph cosecant of x. And we can also graph, what's the reciprocal of cosine? Good. I'm hearing it. It's just quiet. Be bold. We're a family. He's trying to be. We're a squad? I don't know. That's what the mission teams usually call themselves. Exactly. We're a team. How many coaches are begging their players to talk, right? It's not just a teacher thing. Cosecant, what do we do? We bounce off. Where are the vertical asymptotes? Do you remember? We have vertical asymptotes, and then we bounce, 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 bounce off the maximums and minimums. Vertical asymptotes. Yeah, I think some of you were thinking the horizontal asymptotes. Vertical asymptotes are when the bottom is 0, so you could say when 1 over sine, when sine is 0, and sine 0 at the intercepts. So every time sine is 0, so put cosecant on the sine graph just because it's so much easier that way. So vertical asymptotes at pi and 2 pi for cosecant. And then remember the maximums and minimums are shared, except cosecant 1 over. It's going to bounce off. Instead of 1/2, cosecant is 2. Instead of 1/10, cosecant is 10. Not that that's a unit circle value, but that's the idea. Maximums and minimums shared. Maximums and minimums shared. Maximums and minimums shared. And then bounce, bounce, bounce. Secant is the exact same thing, the exact same process, just off of cosine. So all the intercepts become vertical asymptotes. And then we match the minimums and maximums. Oh, that one's not good. You cannot cross a vertical asymptote. That's illegal. And you come, meet, bounce. Come, meet, bounce. Come, meet, bounce. Come, meet, bounce. I guess you could keep going and draw more vertical asymptotes, but that's the idea. Questions on the idea? Get sine, get cosine. Vertical asymptotes are the intercepts, and then bounce. You guys get these are 2 different graphs, right? That's sine, the red. That's cosecant, the green. That's cosine, the red. That's secant, the green. Okay. Now, that's weird. Shouldn't tangent also have cotangent? Tangent, he's different. He's sine over cosine, right? Sine over cosine means for tangent, whenever, sine over cosine, domain problems when cosine is 0, and cosine is 0 at pi over 2 and 3 pi over 2. whenever cosine is 0, which is at pi over 2 and 3 pi over 2, tangent, because that's his denominators, is going to have vertical asymptotes. So whenever his denominator is 0, he's going to have vertical asymptotes. Pretend they're straight. Do better than I'm doing. It's hard drawing sideways. Halfway in between each of his vertical asymptotes, he has his point of inflection. As long as he's non-transformed, it'll be on the axis. Then you guys remember what he looks like? Swoop, there he is. Okay. Swoop. It's concave down, up to the point of inflection, and concave up after it. Going towards his vertical asymptotes. Cotangent's different. He's cosine over sine. So he's going to have his vertical asymptotes when sine is 0, which happens at 0 and pi and 2 pi and 3 pi. So I'm going to go by pi's instead for him, because it's easier. So my units are a little bit different on these two graphs. In between will be the pi over 2's. Cotangent has vertical asymptotes at pi and 0 and 2 pi and negative pi, negative 2 pi. It's kind of like he's shifted. Instead of having them on every half power of pi, other than the even ones, other than the integers, other than the whole numbers. Cotangent has vertical asymptotes at every multiple of pi. In between, just like tangent, he's going to also have points of inflection right on the axis. However, cotangent swoops the other way. He goes concave up before, then concave down after. Concave up before, concave down after. Concave up before, concave down after. Concave up before, concave down after. Okay. I did tangent and cotangent separately just because it's a lot easier if they're separate, because they are, I mean, they're similar, but they're different. And to put them on one graph, we did it last year, it wasn't nice, it wasn't pretty. It was possible. We took all the zeros and made them vertical asymptotes, took all the vertical asymptotes, made them zeros, swooped it the other way. But instead, the graph I want you to add, not to cotangent, he's just going to be himself, just cotangents alone. But tangent, I want you to add in a different color like these, y equals tangent inverse. He's the only inverse we have to worry about as far as the AP goes, so we're just stopping there and not going crazy. He's the only inverse we have to worry about. And tangent inverse, it's kind of hard to show him. Because for inverses, you think, okay, we got to flip everybody. And it's like, if I flip him, he's going to have all these like little swoopy swoops all the way as he goes, swoopy swoop, swoopy swoop, all the way up. And it's going to be nasty. But remember, inverse functions only allow one part. Only one portion, only one region to be flipped. So actually, for tangent inverse, he's only going to have one region. It's going to go to pi over 2. And negative pi over 2, because what was on the x is now on the y, so we have to put our pi over 2 and negative pi over 2. We're going to have horizontal asymptotes for tangent inverse, because he flips. Then all we have to have is one swoop. There he is. Just one. All we need is one. Because that's all that's allowed. That just got nasty. I'll get rid of that. All we need is one. So tangent inverse, just one cycle. Just one period. Flipped. Got him. So, how many graphs? 16. Actually, 18. Why? 16. Actually 19. 16, 17, 18, 19. But 16 total. Just introducing you guys to the idea of a forever quiz. Forever quizzes, quizzes on the forevers. I could do anything like state the entire unit circle, which I probably wouldn't for sake of time, but I could. I could say state the entire unit circle. Or I could say something like, what kind of, no, I won't say that. give me a Pythagorean property, fill in the blank of sine 2x equals, sketch a graph of y equals ln of x. If I were to say that one, y equals ln of x, and if you were to pass if you were to pass the y-axis, I'd have to take off points because there's a vertical asymptote, you can't cross it. So even though it's a sketch, you can't like do an error. You can't have, what's another example? You can't have e to the x go past the x-axis. For sine, you would have to have it meet in the middle, or cosine, you'd have to have it displaced at 0, 1. So even though it is a sketch, it's still a very precise sketch. You wouldn't necessarily need to like label all of these like different radians and whatnot. Well, you should, because you would need to be able to show me that you know where the vertical asymptotes are. But as long as you showed me like one cycle, as long as you showed me one cycle, kind of like what's shown here, that should be enough. I wouldn't ask sine and cosecant. I mean, I guess I could. But for other quizzes, it's anything from state this definition, state this theorem, which is basically like give the whole card, to fill in the blank, like sine of 2x equals, to like give me one little piece of a card, like sketch a graph. So I can ask little things or I can ask big things. Does that kind of make sense in studying? Okay. But I would never, on a forever quiz, be like, sweet, give me all 19 of the basic graphs, and you'd have to come up with, no, I don't care if you randomly can quote all 19 of the graphs. What I care about is if I ask you to think about a 1 over x graph, that it pops into your mind right away. Does that make sense? Right. Yeah, definitely. Sadly, I don't know if I can get this whole page. Do you know what I mean? I don't know if I can get the top totally, but I think you can kind of see most of it. Is that okay? Okay. Then it will be saved in the notes online underneath review forever cards. And it will be on the video. All right, cool kids. So that's you getting it into your notes. Some of you were able to do it into your forever cards at the exact same time, and that's perfect. Some of you were not able to, and that's totally okay. As long as you got it into your notes, copy it into your forever cards a little bit later. P.S. Do you guys like how the screen is a little bit bigger this year? Maybe you didn't notice. It's okay. I'm going with a different view. The sad part is with the different view, do you see how it cuts off? And if you look back here, it cuts off about this much of my screen. So I'm going to do the best I can. I might not adjust every single page. So can we kind of tell this says preview of calculus? Ask me if you can't read it. For those of you guys that are new to my class, this is what notes are normally going to look like on the beginning of a new section. It's kind of like Cornell notes if you've ever seen those before. If you're in AP Gov or AP US History, you're seeing them a lot. In that, I put the key terms in this little column right here. This could just be the natural line in your notebook, but sometimes it's not going to be big enough. So some people make their own line with a ruler or with an ID card. Or just drawing it. Some of you guys can just use the pink line in your notebook, and that's okay. In the top left-hand corner, we put the section number, so section 1.1, and this always needs to start at the top of a new page. It doesn't have to be it can be the back of the page, like the top of a back if maybe you were on the front. But it needs to be at the top. Every new section is always started, like a new chapter is always started, like in a book. Sorry, I didn't actually draw the parallel. In a book, a new chapter, even if you still have more space, is just going to start on a new page. Same thing here. And then in your table of contents, don't you already have section 1.1 preview of, ooh, didn't I say limit? Call it in your table of contents. Oh, I put preview of calculus? Perfect. Chapter 1 was limits. Thank you. 1.1 preview of calculus already in your table of contents. So right now you can figure out what page you're on, and you can go back to the table of contents and fill that in. Like for instance, Thomas I see is on page 4. So he would go back to his table of contents and put down page 4. Some of you guys might be on page 2 or page 3. It just depends. Okay. You might not remember, but we went through a lot of this at the very, very end of pre-calculus, whether you were in honors or in regular. Chapter 12, at the very beginning, we went through a preview of calculus. What I'm about to show you does not need to be written down in your notes. I'll tell you what needs to be written down in your notes, okay? So, preview of calculus. What is calculus? The math of change, of movement, of motion. Blair Thomas. Thank you. You get something free. I don't know what you get, but that's kind of cool. Huh. Welcome to our school. Something free for you in the business office. Okay. Business office is that one if you guys haven't figured out yet. Good. Okay. All right. So everything before calculus was static. What's static mean? Not changing. Yeah, if you're talking about physics, static would be not changing. Dynamic is changing. It's not like static on the radio. Who listens to the radio, but that's okay. It's not like static on the phone, like it starts to go out. It's static as in non-moving or non-changing. Doesn't mean that we never were able to deal with anything with motion before calculus. It just means that we weren't able to deal with varying rates. We had to deal with like fixed rates. We could deal with gravity because it's always negative 9.8 meters per second squared or negative 32 feet per second squared. We could deal with something that's constant all the time, although gravity, depending where you are on the face of the earth, is a little bit different. That's weird, but it's cool. But we couldn't deal with something like you in a car hitting the gas pedal, and not only are you going a speed, but you're going a speed that's changing. We couldn't really deal with that without calculus. Kind of crazy. So let's go through a few things before and after. You don't need to write this down. Okay, before and after. And I think we're going to cover almost everything this year. I'll point out a couple things that aren't going to be seen until BC. But without calculus, we can take a function, we can plug in a c and be like, haha, easy, f of c. Plug it in, you can get out the y value. With calculus, you can plug in a c to a function that doesn't exist and figure out what is being approached. Now, technically, there are tricks that don't technically need the full scope of calculus to be able to find a hole. So you've done those in Algebra 2 and Pre-Cal, but those are just tricks. The actual way of finding it is using a limit. Without calculus, we could do 2 points of a linear function and find the slope, because the slope of a linear function is always constant. But with calculus, we can not just find the slopes or the rates of linear functions, but find the slopes or the rates of varying curved functions with curvatures. We can find a secant line before, we can find a tangent line after. We need 2 points before calculus. We only need 1 and the behavior of the function with calculus. We can figure out average rate before, instantaneous rate after. Average, what's the average over the 3 hours if you spent this much time driving and you went this distance? We could find the average. With calculus, we can figure out the instantaneous. How fast were you going at this time, at that time, at this time? Curvature of a circle, we could figure that out. Circumference or arc length of a circle, that was geometry. But now we can figure out curvature of a curve, something that's not just a normal geometric figure. And that's kind of a pattern that you'll see for the rest of these. We could figure out the height of a curve. We could plug in, like on our calculator, you can find the value by plugging in an x, get the y, no big deal, find out the height. But with calculus, without a calculator, you could figure out for a certain interval what is the maximum value, minimum value of things beyond parabolas. We could stick to geometric figures and figure out things like tangent planes without calculus, but we can talk about other types of surfaces, which maybe if you guys just think about real life, not everything out there is necessarily a perfect geometric sphere or a rectangular solid or pyramid. Usually, things that are geometric solids are man-made. So how do we deal with nature? How do we deal with irregular shapes? Calculus. We can figure out direction as long as it goes in a line. We can think about vectors and other fun things, physics people. But if it's linear, we can think about that without calculus. But if it's, for instance, motion off of a curve or forces off of a curve, we need calculus to deal with that. Geometric before, weird shapes after, constant force before, varying forces after, center of a geometric figure before, center of something weird after. If you can notice, we're just kind of expanding what we're able to do with calculus. And then same thing here. This is a BC topic. This is a college calculus. The AP doesn't even really want to go into it topic when we're dealing with like masses and varying densities and work and things like that. The more physicsy it gets, the more college calculus and the less AP calculus it gets. But we can deal with weird stuff now. Now this is going to be second semester at the very, very end. Well, specifically this one, both. And this is BC altogether. We don't see sequences or series or sums at all. We don't have to do them at all in AP, which is nice. Okay, Here we go. Let's remind ourselves of the two main problems of calculus before we get into it. Tomorrow we're going to do like a quick little group lab sort of thing. So make sure tomorrow at least one person, maybe you want two to be able to double check, has a graphing calculator. You're going to need it tomorrow. You don't need to worry about expos. I mean Monday. You guys know what I mean. Silly goofs. So make sure on Monday, as soon as you guys get in, make sure you have two calculators. I'm going to have a little handouty thing for you guys to grab. You're going to need scratch paper, so I'm probably going to put all of you guys in the back of your homework spirals because that's our nice, easy way of having scratch paper that we don't have to like tear out or get out or have separate from the rest of our information. The back of our spirals will be our workspace. So you're going to want your homework spirals if you are not already bringing them to class on Monday. And you're going to have, each group is going to have one of these. And an expo, and an eraser. And what we're going to do is illustrate with an actual problem how to solve for the tangent line, or for a tangent line, because there are infinitely many tangent lines. Think of a pencil, and this was in your summer packet, wasn't it? A pencil against a curve, that's like the tangent line. We're going to do some solving without calculus, but seeing why we want to use calculus instead, about how to find a tangent line. That's the one big problem of calculus. It's basically all of semester one. It's not the problem that we're solving all of semester one. But the problem, the solution, using limits leads us to derivatives, and then we say, okay, so what's some stuff we can do with derivatives? First of all, it's master even being able to find them. All kinds of basic rules and trying to get down like the product and the quotient and the chain. But then also, how do we use them in word problems? And then we're also going to talk about the area problem and figure out what's going on with that. So on Monday, make sure at least two people have your graphing calculator. Make sure your forever cards are all nice and up to date, and you have your homework spiral. And then we're going to bust out stuff, and it's going to get real normal real fast. Bye, guys. Happy weekend. Get some rest. It's been a long week. You'll need it as we get going. Wished honors pre-cal luck as they come in. They have a graphing calculator quiz. What? Oh, yeah. Remember that one?
I don't want to go because there's so much stuff. I don't want to.
Bye, guys.